Hi, thanks for joining me. Today I've got a really cool number theory problem I want to solve. We want to find all positive integers a and b such that a to the b equals b to the a. So this really cute looking equation here. We want to find all positive integer solutions. Okay, so if you want to have a go at this problem, pause the video now and give it a go for yourself. And I'm going to jump straight into a solution. Okay, so before I get stuck into a solution, I should give a little shout out to Blackpenredpen. He made a really similar video in which he compares e to the pi and pi to the e. I'll leave a link for that video in the description below. Go and check it out after you've watched this one. A lot of the maths I'll be doing in this video is quite similar to the maths in that video. Anyway, let's get stuck into solving this problem. The first thing I guess we notice is that this thing here is symmetric in a and b. In other words, if we swap the roles of a and b, this equation sort of stays the same. So if I swap a for b, I get b to the a on this side, and on the right hand side I get a to the b. But obviously a to the b is that, and b to the a is that. So it's the exact same equation, just written in a different way. So that means if I have a solution, so if, I don't know, xy is a solution, so, oopsie daisy, if I have ab and this thing here, so if xy is a solution to this thing, then also yx is also a solution, just by swapping the roles of a and b. Okay, so we may assume without loss of generality that a is less than or equal to b, because then if a is bigger than b, then that just corresponds to a symmetric solution. Okay, and I guess one thing to look at is the case when a equals b, but if a equals b, this is trivially true. Okay, because on the left hand side we have a to the a, and on the right hand side we also have a to the a. Okay, so that automatically gives us infinitely many solutions to this equation. So I guess we could have this thing here, anything from this set here. So if a equals 1 and b equals 1, a equals 2, b equals 2, a equals 3, b equals 3, and so on. So that's infinitely many sort of trivial solutions, and those are quite boring. But now what I want to do is actually show you that there's only one more, or sort of two more, given the symmetry, so two symmetric solutions, so theoretically just one solution on top of this and no more. Okay, and that extra solution is the case a equals 2 and b equals 4. Okay, so when a equals 2 and b equals 4, this thing here is 2 to the 4, which is 16, and on the right hand side we have 4 to the 2, so 4 squared, and that's also 16. So this thing here gives us another solution, and again we have the symmetric solution, so when a equals 4 and b equals 2. Now what I want to do is prove that there are no other solutions, or no other integer solutions to this equation here. Let's get stuck into that. Okay, so what we're going to do is actually look at a more general problem. So here we're focusing on natural number solutions, but now I'm going to look at a more general problem where I just look at positive real number solutions. So I want to find all positive real numbers, or I want to sort of look at the problem xy positive reals such that x to the y equals y to the x. Of course, any solution to this problem will also be a solution to this problem. Okay, because obviously the positive natural numbers form a subset of the positive reals. Okay, anyway, what I'm going to do to this equation here is raise both sides to the 1 over xy power. So on the left hand side I get x to the y raised to the 1 over xy, and on the right hand side I get y to the x raised to the 1 over xy. Okay, and now this left hand side here, the exponent using exponent rules is going to be y times 1 over xy, which is just 1 over x. So this thing here is x to the 1 over x, and on the right hand side I get y to the 1 over y for the exact same reason. So now we've got a really cool looking equation, and what's really nice about this is the left hand side is exactly a function of x, and the right hand side is just a function of y. So it's sort of, we've separated this equation into a function of x equals a function of y. Okay, now so if we have a solution to this, or a solution to this problem exists if and only if that solution is also a solution to this problem here. And I guess you could ask, well, what if x is 0, y is 0, we might get something ugly in the exponent, but we don't worry about those because we're looking at the positive reals. Now what I want to do is sketch the graph of x to the 1 over x and then analyse its properties, and then we'll see something really nice about solutions to this problem, which will tell us something about solutions to this problem. Let's sketch this graph. Okay, so we want to sketch a graph of y equals x to the 1 over x, and there are two crucial properties that I want to work out about this graph first before I sketch it. Is firstly, what is the behaviour as x goes to 0? So I firstly want to know what is the limit as x goes to 0 from the positive side of x to the 1 over x. And the other thing I want to know is turning points. And I guess the final thing is the limit as x goes to infinity of this thing here. Okay, so once I've worked out these three pieces of information, I can draw a rough sketch of this graph, which again will help us solve the general problem, which will then help us solve that problem here. So firstly, let's work out the limit as x goes to 0 of x to the 1 over x, and to do that we're just going to be using sort of standard tricks, L'Hopital's rule, that sort of stuff. So the limit as x goes to 0 of x to the 1 over x, so this thing here is equal to the limit as x goes to 0 plus. Now I'm just going to rewrite this thing here as e to the 1 over x log x. Okay, so obviously 1 over x times log x, I can bring the 1 over x into the exponent, so that's just e to the log of x to the 1 over x, and obviously e and log cancel, so I'll just be left with this. So this equals this. Okay, and this thing here, what I'm going to do is, because e is a continuous function, I can bring this limit into the exponent. So this equals e to the limit of x goes to 0 plus of log x over x. And now, I guess we can sort of see log x as x goes to 0 plus is just sort of negative infinity. And when we divide by 0 plus, that's sort of the same as multiplying by positive infinity. So this thing here is just minus infinity times positive infinity. So that, of course, sort of goes to minus infinity. Sort of an abuse of language, abuse of mathematical notation there, but hopefully that makes sense. So this thing here sort of goes to negative infinity squared, which is just at negative infinity. So this thing here is e to the negative infinity, which of course is just 0. So I think I said we needed to use L'Hopital's rule. We don't actually in this case. This limit here equals 0. That's great. Now let's look at the other two bullet points. Okay, so the next bullet point I'm going to address is the third one. So we want to know the limit as x goes to infinity of x to the 1 over x. And for this, we actually do need to use L'Hopital's rule, but we're going to use the exact same technique. Write this as e to the something. Okay, so this is e to the 1 over x log x as before. Okay, and I guess one thing I should comment is if you're ever trying to work out the limit and you've got some sort of function of x in the exponent, this is sort of the rule of thumb. Write this thing here as e to the power of something using logs and that sort of stuff. Okay, anyway, let's work out this limit here. Sorry, not 0 plus, to infinity of this thing here. And again, we can bring the limit into the numerator, into the exponent, sorry, because e is a continuous function. So this is just the limit as x goes to infinity of log x over x. But now, I guess one thing we know is that log x over x, x grows bigger than log x. So this thing here should tend to 0, but we can quickly verify that just using L'Hopital's rule, because log x goes to infinity as x goes to infinity, and x also goes to infinity as x goes to infinity. So we can differentiate the top and the bottom. So this is also the same as e to the limit as x goes to infinity of log x. The derivative of that is just 1 over x, and the derivative of x is just 1. So this thing here is just 1 over x over 1, which is just 1 over x. And of course, as x goes to infinity, this thing here goes to 0, so we get e to the 0, so this thing here equals 1. So as x goes to infinity, this limit as x goes to infinity of x to the 1 over x is just 1. Finally, let's look at the turning points of this graph. Okay, so to work out the turning points, we're just going to differentiate this thing here and set it equal to 0, pretty standard. So I'm firstly going to write this as e to the 1 over x log x, as I've done a couple of times now. And now I'm going to differentiate both sides, so dy dx. Okay, just using the chain rule, I'm going to differentiate this thing here, shove it into the front here, and then multiply it by e to the 1 over x log x, which of course is just x to the 1 over x. So the derivative of this thing here, using the product rule, let's differentiate this first. So we get minus log x all on x squared, and then the derivative of this thing here is 1 over x, so then we get plus 1 over x squared, and then we get times this function here, but this thing here is just x to the 1 over x. Like this thing here, and we want to set this equal to 0. Okay, this thing here never equals 0, so we don't have to worry about that. We just need to worry about when this thing in the brackets is 0, but that's precisely when 1 minus log x equals 0, so log x equals 1, so that means x equals e. So that means our only turning point of this graph here is when x equals e, and I'll sort of leave it just as an exercise for you to check that that is a maximum turning point. In other words, that's the highest point of our graph. Okay, now we've worked out our 3 bullet points, let's sketch this graph and go back to solving our general problem. Okay, so here's a graph of y equals x to the 1 over x. So as x goes to 0, this thing here goes to 0, as we worked out. And as x goes to infinity, this thing here also goes to 1, sorry. Hence this sort of horizontal asymptote there. And the maximum turning point is at e. And of course, this point here equals e to the 1 over e. Now, what we want to do is look back at the problem we're trying to solve. So a to the b equals b to the a. And remember, we're sort of assuming a is less than b because obviously once we get a solution for a less than b, we can get the corresponding one just by switching the order. Okay, now I claim that a can't be bigger than e. So why can't a be bigger than e? Well, if we look at this point here, if a was bigger than e, we'd have something like that. So that's a, say. Okay, and so that obviously is a to the 1 over a. But then because b is bigger than a, it means that b is some point to the right of a. But sort of just by looking at this graph, it's clear that b to the 1 over b is going to be strictly less than a to the 1 over a. So that can't be a solution. So we can conclude that a must be less than e. But because we're only looking at positive integer solutions, it follows that either a is 1 or a equals 2. And these two we can just check by hand. In the case that a equals 1, if you look up here, we've got 1 to the b, so that's of course just 1. So on the right hand side we have b to the a, so that's b to the 1. So we require b equals 1. And we've already considered that solution. And then a equals 2. Then on the left hand side we get 2 to the b equals b squared. But again, if we sort of look at where a is here, so where 2 is, sorry. So if we look up to this point here, we can see just by looking across, there's only going to be one other value of b for which this thing holds. And we've already sort of checked that b equals 4 does the job. So that's the set of solutions. It's just the trivial ones plus a equals 2, b equals 4, and of course its symmetric opposite. So that solves our problem. I hope you have enjoyed this video. A nice little number theory one. Anyway, I'll catch you in the next one. Have a great day.